All right. Today we're doing 3-1. Yesterday we started 3-2 and did substitution. Today I'm going to take you back. This one's a little bit easier to teach with me not present. So this is solving systems graphically, and you already know what a system is. So this is going to be a little bit easier strategy, but it doesn't work all the time. But it's one that you should have in your toolbox. All right, so systems of equations. Like I said, I know we already we talked about those yesterday, and you're pretty clear on what those are. But system of equations, okay, is when we're solving several equations containing two or more variables simultaneously. Okay, so it might have an x and a y, an x, y, and a z. They might have an a and a b. Okay, a solution to the system is the set of points, okay, that make all the equations in the system true. Again, they make all the equations in the system true. This is one method to find their intersection by graphing. So you're going to have three by the time we're done. You're going to have graphing, substitution, and elimination. Okay, so this one we're going to start off solving the system graphically. So we're looking for that one point where they intersect and all of the equations are true. It's always that point of intersection. So the first thing we're going to do is graph each equation, and then the answer is the point of intersection. In order to graph these, we have to put them in either slope-intercept form, or we have to find their x and y intercepts. So you can do either one. Doesn't matter, but I'll show you one versus the other one. So this one, let's use, we're just going to use the intercepts. Okay, so that's where we plug in 0 for each one. All right, so if we're looking at the equation x plus 2y equals 4. Okay, so we're going to plug in 0 for x plus, so I have 0 plus 2y equals 4. So the 0 doesn't really exist. We divide by 2, and we have y equals 2. So we have a point at 0, 2 to graph. And then the other equation, we're going to plug 0 in for y. So we're going to have 0, or sorry, said 0 in for y and had 0 on my mind, so I wrote it. Okay, so we're going to have x plus 2 times 0 equals 4. Okay, well 2 times 0 means it's not there, so we just have x equals 4. So our ordered pair here is 4, because that's our x, and 0 is our y, because that's what we plugged in. All right, so we're going to have 0, 2, so 0, 2, and 4, 0. 1, 2, 3, 4, 0. So hopefully your graph, it's really hard to graph on this thing. I'm terribly sorry. Hopefully your graph looks better. All right, let's look at the second equation. 2x minus y equals 3. Same thing. We're going to use our intercepts. We're going to plug a 0 in for x. So 2 times 0 minus y equals 3. So 2 times 0 is just 2. But we have this negative y. Well, we can't have that, so we need to divide by negative 1. So we have y equals negative 3. So our ordered pair here is 0, because we plugged that in for x. Our y is negative 3. This is stuff from last chapter that we're pulling in this chapter, so hopefully you're following, because I'm moving pretty quick. All right, now we're going to plug a 0 in for y. So we're going to have 2x minus 0 equals 3. Okay, well, minus 0, that's not really there. So we have 2x equals 3, so we can divide by 2, and we get x equals 3 halves. There. So our x is 3, our x value is 3 halves, and our y value is 0 this time. So a little bit harder to graph that way, but we can do it. So 0, negative 1, 2, 3 is 1 point, and 3 halves is 1.5 and 0. So doable, but a little difficult. Okay, let's see if I can do a better job graphing. Better. Not perfect, but better. Okay, so we have graphed each equation. Now we need the point of intersection. So we have our answer. So our point of intersection is right there. Okay, and that point of intersection is over 2 and up 1. So our solution, I hate to write in this yellow because I'm not for sure you can see it, so let me change it. So the solution is 2 comma 1. Our solution is 2 comma 1. And it's that point where they intersect. Okay, so again, there's two different strategies to solve it even graphically. We can use the intercepts like we did here where we plug the 0 in for x and the 0 in for y. Let's look at the next example and we'll use slope-intercept form on it. So we're going to solve this system graphically, but this time we're going to use slope-intercept form. So I'm just going to take each of these equations and put them into slope-intercept form. So I've got 2x plus y equals 0. We're going to subtract 2x from both sides and have y equals negative 2x plus 0. So I don't need to do that. Okay. So there's our equation, y equals negative 2x. I'm going to go back up here and write as a reminder. Slope-intercept form is that y equals mx plus b. I'm sure you guys are really good at this by now, but I want to do that. So let's graph this. Our y-intercept is 0. Okay, so we're going to have a y-intercept at 0. And then our slope is negative 2. So I'm going to go down 2 over 1. Down 2, right 1. I shouldn't just say over. I'm actually going to go back and go up 2 and left 1. Up 2 and left 1. Because I like to have a lot of points. It makes my graph a little bit nicer. You don't have to do that. Okay? And the next equation. 3x plus 2y equals 2. Again, we're going to put it in the slope-intercept form. So I'm going to subtract my x's, 3x from both sides. So I have 2y equals negative 3x plus 2. I'm going to divide by 2. Y equals negative 3 over 2x plus 2 divided by 2 is 1. So here is my formula for that equation. So my y-intercept is 1. Put that there. My slope is negative 3 over 2. So 1, 2, 3 down, and 1, 2 to the right. Negative 3. Yep. So 1, 2, 3 down is my negative, 2 to the right. Again, I'm going to go back up. Go up 3 this time. 1, 2, 3, and left 2. Hey! So these lines are like super close together. Super close together. Again, really cruddy graphing there. So sorry. And my point of intersection, though, is right there. That's my solution. That is the solution. So here, our solution is going to be negative 2, 1, 2, 3, 4. Negative 2, 4 is our solution. It's that point of intersection. Okay, so hopefully, again, you can kind of get a choice of how to solve it. There's two ways to do it graphically. You can do it by the intercepts, which we did example 1, or with slope-intercept form in example 2. I will tell you this is the method that I prefer because I feel like I am quicker at slope-intercept form. And I don't have to solve the equation 4 times. I just have to solve, or I don't have to solve each equation twice. I just have to solve it the one time. I prefer that, but you can do whichever one you want. Okay, so flip over to the back. Let's look at some more good stuff here. So we have some types of systems. This is why this is part of why this is taught first, instead of me skipping around yesterday, but that's okay. All right, so our types of systems. All right, so first of all, the system is either consistent and independent, which we say IC, because it's independent, consistent. or it's consistent and dependent. So that's DC, dependent, consistent. But there's two types that are consistent. All right. And then the other type is inconsistent. We just say I. So if it's independent and consistent, there's one solution. We're looking at the solutions now. There's just one solution. So it's that point of intersection on the graph. A dependent consistent has an infinite number of solutions. So it's written with that set notation, right? Our x, y is such that y equals, and you write the graph, negative x plus 3. And it's in those braces because it's set notation. Okay. In this case, if you look, these lines are right on top of each other. So there is one, and then there's another line. I've tried, it's the exact same line. So they match up, and so every point on the line is a solution, which is why there's an infinite number of solutions. In the inconsistent, there are no solutions. These graphs, these lines are parallel. They will never intersect. So there's no solution in those. Okay, the other thing is we have a slope-intercept comparison. So in an independent consistent, the slopes are not equal to each other, right? The slope of the first one is not equal to the slope of the second one. In a dependent consistent, the slopes are equal and the y-intercept is equal. Okay, and in the inconsistent, they have the same slope because they're parallel, but their y-intercept is different because it's in a different place on the coordinate graph or on the coordinate plane. Okay, so you can look at those things. But if the slopes are different, then you know it's that independent consistent and you're only going to get one answer. If the slopes are the same, like in the dependent consistent and the inconsistent, then you have to also look at the y-intercept. Okay, so keep this chart handy as we're going through and doing some classification. All right, so let's do example 4 and do some classification. You're going to have it handy on your page to look at, me not so much. Okay, says classify each system as independent consistent, dependent consistent, or inconsistent. So again, I'm great if you put IC, DC, or just I. All right, so if we're going to do these, we have to look at the slopes and the y-intercept. So we might as well put them in slope-intercept form so we can do that, right? Like that kind of makes some sense there. Okay, so the first equation, we've got 3x minus y equals negative 1. We're going to get it in slope-intercept, so subtract 3x. Then I have negative y equals negative 3x minus 1. I can't have a negative y, so I'm going to divide by negative 1. I end up with y equals 3x plus 1. Okay, the other equation, let me change colors. Maybe I can sort it up. I don't want red, I just had orange. There we go. Okay, so my other equation is 2x. Well, I thought I tried to change it to blue, but obviously I didn't. 2x plus 3y equals negative 8. So we're going to subtract 2x. Then we'll have 3y equals negative 2x minus 8. Divide by 3. And we have y equals negative 2/3 x minus 8/3. Yes. Okay, so here we go. The slope here is 3. The slope here is negative 2/3. Well, if the slopes aren't equal, right, M1 is not equal to M2, we know, hey, it goes in this column, which is independent consistent. So IC. Okay. So let's change up and do B. Same thing, we're going to get them in slope-intercept form. All right, so 9x minus 3y equals negative 6. Lots of practice for these writing equations. So we've got negative 3y equals negative 9x minus 6. Divide by negative 3. Y equals 3x plus 2. All right, let's change it up. We'll do the next one. 6x minus 2y equals 4. We're going to subtract 6x. I've got negative 2y equals negative 6x plus 4. Divide by negative 2. So then I have y equals positive 3x minus 2. All right, those are close, right? Very close. The slope up here, m equals 3, and the y-intercept, I should go ahead and identify those, is 2. In the equation down here, we have the slope equals 3, but the y-intercept here is a negative 2 because it's minus 2. So in this problem, m1 is equal to m2. However, b1, our slope, or our y-intercept, and b2, our y-intercept, are not equal. If that's the case, then this is